Hello everyone, welcome on this e-learning platform of Apex Institute of Physics. In the previous video you have seen or you have learned rather the electric potential and its basic formula. Now we will be using those formulas to find the electric potential because of various charge distribution. In this video we will start with the finding electric potential due to discrete charge distribution. So when the charge distribution in the form of discrete manner. So idea is like if we have let's say this is a point charge q1 and there is another point charge q2, there might be another point charge q3, and you might be asked to find out the potential, net potential at point P, which is somewhere there. So what we need to do, we need to join this q1 with the location of that point P. Let's call this distance as r1. Because of this charge q1 there is the potential going to be, let's call it v1. Similarly we will join this point charge q2 to that point and we will call this distance as r2, that will be known to you. So this q2 and r2 will decide the potential v2 at this point P. And similarly if we join that location with the point charge q3 and this distance is r3, so v3 can be calculated. That means we can calculate potentials because of individual charges. Then the total potential at the point P is going to be V is equal to V1 plus V2 plus V3. If there are more charges, so we will keep on adding in this manner. So in case of discrete charges, we will find the potential because of individual charges and we'll be summing them up. Now what the V1 and V2 and V3s are going to be, we have understood because of a point charge. The formula is V, let's talk about the V1. So V1 is going to be K Q1 upon R1. Similarly we can find V2, we can find V3 and all that, we can add them up. So that's a rule we need to follow. Let's see by an example the application of this part. So here is an example. Let's say we have a given charge distribution Q, 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 Q. The all charges are located at the vertex of a square. Let's say square has a dimension A, so that's also A. This dimension is also going to be A. And there's a point, center point O. And the question is find electric field and electric potential at the center of this given charge distribution. So let's first find the electric field because we have understood what the electric field is. So we know the electric field, total electric field at the point O is going to be because of individual fields, and we will make the vector sum of them. So there are three fields, rather four fields that have to be written and we need to sum them up. We know as per the rule, if we call them as a like this is 1, 2, 3, 4. Let me number them so that we can easily identify. Let's say this is number 1 charge, this is indicating 2 charge, this is indicating 3rd charge, this is indicating 4th charge. So we know the fields of 1 and 3 will cancel out each other and field of 2 and 4 will cancel out each other. So the total sum of this field is going to be equal to 0. So the net field at the center point will be 0 because the vector quantity, so vector sum will be 0. Now as far as the potential is concerned, so we will write potential is going to be V1 plus V2 plus V3 plus V4 in a very similar manner. But this is a scalar quantity, so it does not deal with directions. V1 will be equal to K Q upon the distance of the charge from that point, which is going to be A by 2. That will be going to be let's say this distance is indicated by R for the time being. We will be substituting later on. So that's going to be K Q upon R. Second will also be equal to K Q upon R. Third will also be equal to K Q upon R. And similarly the fourth will also be equal to K Q upon R. If we sum off of all of them, so the total potential will be equal to 4 times K Q divided by R. As far as this R is concerned, we can think of this diagonal is going to be A root 2. So R is going to be half of A root 2. which is going to be basically a by root 2. So we can place in terms of A value. So this final answer will become here V is equal to 4k q divided by A by root 2, which will become equal to 4 square root of 2 kq upon A. So this is how we can find out the potential at that center point, and we have already calculated the field, which came out to be 0, and potential came out to be 4 root 2 kq upon A. Now something we can interpret over here, if the field at any point is 0, that does not mean the potential is going to be 0. So field 0 at any point does not ensure the potential to be 0. Similarly, vice versa, if the potential at any point is coming to be 0, we cannot claim the field is going to be 0, even though we got this relation. So one should not get confused with this relation, and one should use this relation very carefully because it uses the limits from infinity to that particular location. So if the field is 0 at a particular location, at that location we may not be 0. Now V will be 0 if the field is 0 in all the locations running from infinity to R. So here at this O point, E came out to be 0. So E came out to be 0, but V is non-zero. So that's understood, because this is a sum of so many terms. If 2 terms are 0, that does not mean the entire term is going to be 0, right? So this is for the discrete charge distributions. If the discrete charge distributions are given to us, we can find the individual potentials, sum them up, we will get the total potential there, right? And that is one example which is sufficient. Now we will talk about the potential because of continuous charge distributions. So there is let's say charge ring, and we are interested in finding the electric potential due to that charge ring. And let me draw a ring for that matter. So let's say we got this ring which is uniformly charged, and the total charge on this ring is, let's say, Q, and it got radius R. So this ring has a charge Q and its radius is R, and let's say that's a center point. We are interested in finding the potential at the center. So at center, we know the potential as per the definition is K integration dq upon R, using the finite element method. That means we are considering a element or an element which is of dq charge, and if we measure this distance of that element from the center is going to be small r, we will find that small r is equal to capital R. So small r is a fixed number. Since small r is a fixed number, so this will become equal to K integration dq divided by capital R. We know constant terms can be taken outside, so it becomes K divided by R integration dq. Now integration dq over the complete loop will yields total charge. So from here we will find V is equal to K, the total charge, divided by R. So that's going to be the potential at the center of a charged ring. Now we can further interpret this result, since it has came from this integration, which is integration dq, and we know integration dq is going to be equal to Q irrespective whether the charge distribution is uniform or non-uniform. That means this formula will be true for both cases, for uniformly charged ring as well as non-uniform case. So in case the charge distribution is non-uniform, both will have non-uniform or it is uniform, the both case will have the same formula. So potential at the center of a ring, whether the charge is uniformly distributed or non-uniformly distributed, formula came out to be kq upon capital R. Now we know in case of electric field, if the charge distribution is non-uniform, we may not get the same field at the point O, but potential remains the same. right? So that's an important aspect we need to keep in mind. Moreover, if we consider half of the ring or any segment of the ring, the formula will remain the same. It will remain as V is equal to K, the charge available, divided by R, because we know in this ring charge distribution the distance will remain constant, and we have already talked about when the distance of the charge from a interesting point is constant, formula is always KQ upon R. But in that case we need to keep in mind Q has to be the charge on that loop. That means if we have this part of a ring, which may be any segment of the ring, if the total charge now is Q, radius is R, still we will have a potential V is equal to KQ upon R at this center point, which is point O. Again, this charge may be uniformly distributed as well as non-uniformly distributed. So at the center we will have a KQ upon R, where the Q is the charge on the ring. Ring may be half or complete or any part of it. The charge distribution may be uniform or non-uniform. Now let's see the electric potential on the axis of a uniformly charged ring. So let's take this is a charged ring, so the charge is Q, radius is R. There is a point P. We are interested to find the potential at this point P, and let's say this distance is x, which is being measured from the center of this. Again, we will start with writing having a small element dq may be there. Because of this dq, we will like to join this point to the point P, and we will consider this distance to be smaller. Again, we will see with respect to this point P, all the charge will be at the same distance r apart. So on the axis of a ring, the electric potential V be equal to K integration dq upon R. Here we can take this R outside, so it will become K upon R integration dq. Hence answer will become V is equal to K total charge upon R. Again, this charge will not depend whether this is uniformly distributed or non-uniformly distributed. So all type of distributions answer will remain this. However, here this R can be written as under root R square plus X square by using Pythagoras theorem on a right angle triangle. If we join this will become the radius, and this is a right angle triangle. Hence the formula of potential on the axis of a charged ring in case of uniform as well as non-uniform is equal to K Q divided by square root of R square plus X square. So this will be valid for all type of charge distribution on a ring. So again, an important result that has to be understood, remembered. So this is the potential on the axis as well as the center of the ring. We can interpret this result as well, and we can say now V will be maximum on the center point. So we will say the potential or V is max when X is equal to 0. So this maximum is achieved when X is equal to 0, that means at center. And what that center point potential is, if somebody asks what Vmax is, so Vmax is going to be equal to KQ upon R. Otherwise it decreases. So potential is maximum at the center. As we move to away from this loop, potential decreases. Similarly, it decreases in that direction, right? So this is the potential of because of a charged ring. Please do remember, follow it. Thank you for watching. Have a good time.